Hello and welcome to this video presentation. The topic that we have chosen is the first law of thermodynamics and its practical implementation. This is an assessment for the sessional test 3 of the subject thermodynamics, subject code ME205, our subject teacher being Shikha Bhuiya ma'am, submitted by me Abhishek Kumar Kaur MEB19002 and my friend Biswajit Karmakar MEB19003. We are the Btech 4th semester mechanical engineering students of Tezpur University. Law of conservation of energy. It states that energy can be neither created nor destroyed. The first law of thermodynamics is merely one statement of this general law with particular reference to heat energy and mechanical energy, that is work. First law of thermodynamics. When a system undergoes a thermodynamic cycle, then the net heat supplied to the system from the surroundings is equal to the net work done by the system on its surroundings. Mathematically, it can be represented as equation number 1. Now, the application of first law to a process. When a process is executed by a system, the change in stored energy of the system is numerically equal to the net heat interactions minus the net work interaction during the process, as represented in equation number 2. Mathematically, the del E represents the change in total internal energy. If the electric, magnetic and chemical energies are absent and changes in potential and kinetic energy for a closed system are neglected, the above equation can also be written as equation number 3. Generally, when heat is added to a system, its temperature rises and external work is performed due to increase in the volume. The rise in temperature is an indication of increase of internal energy. Therefore, heat added to the system will be considered as positive and the heat removed or rejected from the system will be considered as negative. Now, the application of first law to steady flow process. In many practical problems, the rate at which the fluid flows through a machine or piece of apparatus is constant. This type of flow is called steady flow. Certain assumptions have been made in the system analysis and thus the steady flow equation have been obtained as expressed in equation 4, where C is equal to the velocity of the fluid, Z is equal to height above datum, P is equal to pressure of fluid, U is equal to internal energy per kg of fluid, and PV is equal to energy required for 1 kg of fluid. The energy equation for a steady flow system can be given as in equation number 5, where this equation is applicable to any medium in any steady flow. For non-flow process, the equation is given in equation number 6. The internal energy is a function of temperature only and it is a point function. Therefore, for the same two temperatures, change in internal energy is the same whatever may be the process. For the same value of Q, that is heat transferred to non-flow and steady flow process, and for the same temperature range, we can equate the values of equation 5 and 6 for Q minus delta U and thus obtain equation number 7, where W is equal to the work transfer in flow process and integration of P dot dV from point 1 to point 2 is equal to the total change in mechanical energy for reversible steady flow process. Moving on to the engineering applications of steady flow energy equation. To name a few are water turbine, centrifugal water pump, condenser and steam nozzle, from a list that goes on and on. To begin with, let us have a close look at water turbine. The following image on the screen gives us a schematic diagram of water turbine. The dotted lines enclosing a box represents the boundary. For us in this case, inside the boundary is the system comprising of the water turbine, outside which there is the surrounding comprising of the turbine shaft, the generator on the left. Z1 represents the height from the datum and Z2 is equal to 0 since it lies on the datum. In a water turbine, water is supplied from a height. The potential energy of water is converted into kinetic energy when it enters into the turbine, and part of it is converted into useful work, which is used to generate electricity. Considering the center of turbine as shaft as datum, the energy equation can be expressed as given in equation 8, where W is positive because work is done by the system. Now let us look at the uses of water turbine. Water turbines are used in hydraulic power generating plants. where it converts potential flow energy contained in water into mechanical energy. This mechanical energy is subsequently converted into electrical energy in a generator. The gear units for water turbines gear up the low turbine speed into a very high generator speed. They also convert the torque, that is the output by the turbine, and transmit it into the generator. Next in application, we have the centrifugal water pump. The schematic diagram of centrifugal water pump is shown on the screen. The rectangular dotted line enclosing a box represents the boundary which separates the system from the surrounding. The system constitutes the centrifugal water pump as shown in the middle, and the surrounding constitutes of the electric motor on the left hand side and the water to be pumped. Z1 and Z2 are respective heights from the datum. A centrifugal water pump draws water from a lower level and pumps to a higher level as shown in the figure in the previous slide. Work is required to run the pump, and this may be supplied from an external source such as an electric motor or a diesel engine. Here in this case, heat transferred, that is Q, is equal to 0, and change in internal energy, that is delta U, is also equal to 0, as there is no change in temperature of water. V1 is equal to V2 is equal to V. So applying the energy equation to the system, we obtain equation number 9. The sign of W is negative because work is done on the system, or we can say work enters the boundary. Coming to the uses of it, they are used often in oil refineries and power plants. They can be used for boiler feed applications, wastewater management, flood protection, drainage and irrigation. The chemical and process industries use centrifugal pumps for applications such as paints, petrochemicals, cellulose, hydrocarbons, food and beverage production, and sugar refining. The mining industry uses centrifugal pumps as froth pumps, separating bitumen and minerals from clay and sand. They also use them to transport solids and slurries. That's it from my side. Over to Biswajit.
Myself, Biswajit Karmakar, would like to continue with the remaining slides. So let's start with the condenser. Now if you look at the diagram of the condenser, then we will find that the steam is entering through the upper pipe and it is condensing out through the lower pipe. Similarly, the water is entering through the left pipe and it is coming out through the right pipe. Now the part which is enclosed inside a box, that is considered as a system. So the purpose of the condenser is to receive the high pressure gas from the compressor and convert this gas to a liquid. Now in condenser we usually take potential energy and kinetic energy equal to 0, as their value are very small compared to with enthalpies. Work done also 0, since neither any work is developed nor absorbed. Now if we put this value on energy equation to the steam flow, then we will find that the change in enthalpy is always equal to heat loss by 1 kg of steam passing through the condenser. Now we can write heat as a mc delta T, where m is a mass of the cooling water passing through the condenser and C is specific heat of water. Now the uses of the condenser are refrigeration, air conditioning, and in steam power plant. So the major type of condenser are water cooled, air cooled, and evaporative. Now the next part is steam nozzle. In steam nozzle, we will find that it has a converging part and diverging part. The steam is entering through the converging part and it is coming out through the diverging part. The part which is enclosed inside the box is considered as a system. Nozzle is often a pipe or a tube of varying cross-section area, and it can be used to direct or modify the flow of fluid, and also used to control the rate of flow, speed, direction, etc. Now in nozzle we usually take potential energy, work done, and heat is equal to 0. Applying the energy equation to the system, we find that C2 is equal to under root C1 square plus 2 into change in enthalpy, and where C1 is the inlet velocity and C2 is the outlet velocity. Now we find that C2 is very greater than C1, then we can neglect the part of C1 and we can write C2 is equal to under root of 2 delta H. Now the uses of the steam nozzle are used in steam and gas turbine, jet engine, rocket motor. It is used to measure the discharge of the fluid, example venturimeter. Injector for the pump feeds water to the boiler. Rocket for providing sufficient thrust to move upward. For removing the air from the condenser using the injector. Steam jet refrigeration system. Now next is unsteady flow process. So there are two common use case for unsteady flow process are: number one is filling a tank, number two empty a tank or tank discharge. So before going to the application, I would like to explain what is unsteady process. Unsteady process is a process in which the rate of mass or a volume on a control volume is increasing or decreasing with respect to the time. For example, if we see on the figure in the slide 13, we see that the mass entering to the control volume is m dot, and there is a no mass leaving the control volume. So from this what we can conclude that the mass is increasing inside the control volume and it is increasing with respect to the time. Means there is a unsteady flow process going through that control volume. So this is an unsteady flow process. Now let's come to the application part of unsteady flow. Filling a tank. Filling a tank is used in filling LPG gas that we use in our household work. In this condition, one system is there, the valve is there, and our pipeline is there. The LPG gas is coming through the pipeline and it is entering the system, which is LPG gas, and there is a valve which is to control the flow rate of the gas, and we can see that the mass inside the system boundary is increasing with respect to the time, and at some point the container will be get full and we will close the valve so that no more mass enter on the boundary, and with this we can use the process of unsteady flow. Now the next application of unsteady flow process is emptying a tank. To empty a tank, we need to just reverse the process of filling a tank. In this condition, we will consider a tank which is full and we will open the valve. After opening the valve, we will find that some gas is leaked through the valve, and due to that leakage, we will find that the mass inside the tank get decreases, and we can empty the tank after some time. So this is the application part of the unsteady flow. So with this, we would like to conclude our presentation. Thank you.